Hello, everybody, and welcome back to another edition of zkStudyClub. Today, we're very excited to have the Ulvetanna team presenting Binius, Snarks over binary fields. And we have Ben Diamond, who's going to be leading the presentation. We have Jim Posen also here as well, who's going to be helping answer questions. Ben, Jim, thank you for being here. And Ben, go ahead and take it away.
Cool. Well, thanks for having me. Glad to be here. And glad to present about Binius, Snarks over binary fields. As you said, this is a joint effort by Ulvetanna, and will be presented by myself, Ben Diamond, and with collaboration from Jim Posen. So just to sort of start to get into things, I can say a few words about the landscape of Snarks that we are stepping into. Just a few rough remarks. Essentially, you can write down a rough categorization of modern Snarks into two categories. The first depends on elliptic curves. So these tend to have extremely small proofs, say constant size, and very cheap verification, say constant time. And for the prover, of course, they're slower. They tend to have trusted setups and depend on either discrete log type or so-called knowledge of exponent assumptions. As for aggregation, they do allow certain kinds of folding, often depending on cycles of curves. The primes over which arithmetization happens are large. They're the scalar fields of elliptic curves on the order of 256 bits. And the bottleneck is computation. I can point to a second category that's become much more prominent in the past couple of years that we could call Starkish protocols. So these depend on only on hash functions and typically error correcting codes. They tend to be sort of unconditionally secure in the random oracle model, subject in certain cases to coding theoretic conjectures, but not all. Many cases, no conjectures. The proofs are larger, on the order of 100 kilobytes, obviously slower to verify. Much faster for the prover. There's a recursion story that is sort of simpler in that the field you use to arithmetize the recursion can be the same field that you used to generate the inner proof. Supports more flexible types of fields, like small fields on the order of 64 or 32 bits. And what we found at Ulvetanna implementing many things is that actually bandwidth turns out to be more of a bottleneck than computation is. So specifically, the problem of physically moving the data, say the witness or some kind of trace from a host into a device like an FPGA, becomes actually more costly and time-consuming than the actual computation. This is just because they're much more computationally cheap. So the bottleneck turns out to be something else. So what can we say holistically about the landscape? For example, we live in a world where recursion is practical and is used routinely in deployed systems today, where the Poseidon hash, so as a sort of byproduct of this, Poseidon, which is a sort of prime field algebraic hash, has become standard. This is because it's sort of more arithmetization friendly than classical hash functions are in the prime field setting. So we'll come back to this. And also lookup arguments are now, especially with the advent of Lasso, and we'll say more about this too, are becoming more practical relative to the other components. And this also is important for us because it allows us to efficiently deal with things like unsigned integer multiplication, which has been or would have been in the past cited as a reason not to use binary fields, but that reason is no longer applicable. So we'll get to all this in due time. Here's a diagram of a live deployed SNARK system today. This is due to Polygon. You can see that there's all sorts of batching, recursion, sort of multiple levels of recursion, things like that. Okay, so just a few more remarks about current snarks. So here's a breakdown of the Polygon zkEVM prover. You can see that Merkleization is essentially the dominant cost, although not by too much. This essentially entails hashing a giant matrix column-wise using Poseidon. We can point out that Poseidon is significantly slower. Actually, this 5x, I think, is more like 9x or more slower than Keccak is on a CPU. There is a further phenomenon called embedding overhead, which has many sort of guises, but one that I can point to now is this idea where you have a circuit whose wires, in principle, could take values up to, say, 64 bits large, but where in actual practical use by an honest prover, they take only 0 or 1 value, right? So, for example, Starkey's Keccak circuit has a bunch of columns, around 2,500. Of those, the vast majority end up only actually being either 0 or 1 during honest proofs. So this is obviously a source of waste. Okay, so with all this in view, can we do snarks over the smallest possible field, namely F2? And again, the two rough reasons why we want to do this, very roughly are, first of all, to lessen the amount of data we have to send. So if the information content is only bits, we don't want to be sending 64 bits sort of logical data, of physical data per sort of bit of information. And also, can we reduce computation? So just a very brief historical remark. So binary field snarks have been brought up before. The original Stark paper by Ben Sasson, Bentov, Horesh, Ryabzev was actually written over binary fields, as was Fry and a few other things. So very roughly, there are some things that work sort of out of the box already in binary fields. For example, there is an entity replacement or analog in the binary setting. This is so-called the additive NTT. So this is due to Lin Chung Han 14. Fry, of course, does work for binary fields perfectly well. In fact, the original Fry paper wrote the protocol in the binary field setting. So certain things don't work sort of naively, right? The most obvious one is this idea that in deep Ali style protocols, you have a sort of multiplicative trace domain. And you have this way for the verifier to algebraically sort of iterate through this domain, essentially multiply by a multiplicative generator of this domain. It is not clear what the analog of this should be in the binary field setting. So here, if your domain is, say, an additive subgroup of your binary field, there is not any obvious algebraic operation whose action on this domain sort of iterates you through it. There's something sort of that kind of looks like this in HyperPlonk, which we'll come back to. This turns out to be not quite enough, but we will have more to say. So the second major thing, and we'll come back to this too, is that Reed-Solomon codes need to have a large alphabet. So the alphabet needs to be as big as the block length is. This prevents you from writing down, say, a binary Reed-Solomon code whose alphabet is just F2, right? It just doesn't exist. So what you end up finding in practice is that in order to use Reed-Solomon at all, you need to do some kind of embedding where even if your message has coefficients that are just 0 or 1, you need to sort of tacitly embed those into, say, F2 to the 16 before Reed-Solomon even makes sense. And of course, your code word will not have bit components anymore. They'll be F2 to the 16 elements. So that's like a 16-fold blow up in your size. Maybe we can use Brakedown with a true binary code with alphabet actually F2. This turns out to have its own problems. So in short, it's not quite so simple a picture of whether we can make this work. We do make this work by essentially answering these questions. So we'll get into how we do that. Okay, so that essentially concludes the introduction and technical sort of historical remarks. Looking forward, this begins the actual sort of content. I can tell you what's what's coming ahead is essentially, so I'll describe how tower fields work. These are a type of binary field, how they work, why we use them. I'll describe our polynomial commitment scheme, how we get away with using Reed-Solomon codes and not having embedding overhead. So this is a sort of key inner component. Moving outwards in layers of abstraction, I'll describe what we call certain virtual polynomial constructions, shifting, packing, things like that. Putting all these ideas together, I'll describe how we do unsigned addition and multiplication, even in the binary field setting. And finally, Keccak, and also some benchmarks. Okay, so let's get right into it. So what are binary fields? Just a rough overview. So essentially, an element of a binary field looks like this. It looks like a string of bits, D bits, let's say, where D is the sort of degree of the field extension. So we can think of it as something like 128. An important fact is that every such string of D bits is a unique or distinct field element. So this is not true for prime fields. You have this wraparound phenomenon where, bit strings representing integers greater than or equal to your modulus are sort of non-canonical or non-unique, and actually, are identical in your field to something else. Addition is XOR. Okay, so very simple. How does multiplication work? Well, we need to say sort of what these bits mean. In the classical case, essentially, we have a univariate quotient ring. Okay, so we start with the polynomials over F2 and quotient this by the ideal generated by something irreducible of degree 128 or D. So the actual elements of our ring are essentially degree 127 or lower polynomials, and these bits are the coefficients of the polynomials. And to multiply 2, we essentially do that multiplication in this ring. So we need to multiply them as binary polynomials and then reduce modulo this polynomial. Okay, so that's how it's typically done. And we're actually going to do something completely different. So let's say what we do, and then later I'll say why we do it. So we're again going to take a bit width, which now has to be a power of 2. Okay, so again, let's just think 128. And as before, this is my F2 to the 128 element, this string of bits. But now I actually have a kind of recursive, so field addition is again XOR. As for multiplication, we have a recursive way of sort of splitting these into two F2 to the 64 elements. Okay, and the claim is that this is not just a superficial thing I did to the bits and sort of break them in two parts. This is actually sort of the makeup of my original field element. My original F2 to the 128 is actually made of two F2 to the 64s, which come from the next field down. I'll say what that really means in a bit, okay? But this sort of keeps going, F2 to the 32 and so on and so forth until we get to the level of bits. And essentially, it's this recursive makeup that will be used in our multiplication. Just to give you a rough picture of what the actual algorithm looks like. So if I want to multiply blue and red, I have my breakdown. So I split them both in half. And the claim is that if I can come up with a way of multiplying the smaller field down, so F2 to the 64, if I can do that, then I can sort of multiply these low halves, so blue's low half and red's low half, and also blue's lower half and red's upper half, and sort of so on and so forth. There are 4 cross terms. If I can do these, which I can use recursion because they're a smaller problem, if I can do that, then I can combine the results using some linear amount of further work and get the answer. Okay, so I'm going to argue, first of all, that we can actually reduce this number of 4 to 3 using a Karatsuba type technique. But we need to say what these additional operations R in order for this to sort of have any content. Okay, so essentially, let's just say this a bit more rigorously what we do. Okay, so we want to build up our field iteratively, sort of inductively. So if we start with F2, first step is we're going to do a univariate quotient like we usually do by something of degree 2, okay, not of degree D in one shot. We just go with a degree 2 extension. This gives us F4. And this ring is a perfectly good field in its own right. So we can iterate this process. Now we have a univariate polynomials in X1 whose coefficients come from T1. And we again quotient this by something, essentially this polynomial here, which I'll say more about in a bit. And this process is something I can repeat until I get to T iota, let's say, which looks like this. Okay, so the pattern is essentially each indeterminate x iota minus 1. I take that squared times the previous indeterminate times x iota minus 1, and then plus 1. And the claim, this is due to Wiedemann 1987, is that these FIs, the ones that I just wrote down, are irreducible forever. Okay, so we don't, so essentially none of these is going to split over the last field. So these actually are fields as desired of the right structure and so on. Now, it's great that these are irreducible. It sort of means that they are fields, but actually we can say more. This particular choice of irreducibles actually has a nice computational sort of setup too, in that we can do arithmetic in these rings actually more efficiently than we can for generic Fs. This was noted by Fenn and Parr in 97. So they give a way to do multiplication in these rings of complexity n to the log base 2 of 3. So this is sort of the Karatsuba exponent. And even inversion. So this is actually a very crazy fact. Inversion is actually barely more expensive than multiplication is in these towers. Okay, so why use towers? Well, essentially, the entire talk will sort of keep coming back to reasons why our use of towers is good, but I can just say a few things right now. So in the classical definition, so first of all, we want to be able to write programs or circuits where intermediate sized fields get used. So 32-bit values or 8-bit values, for example, in the case of Grøstl, as it's called. And also Reed-Solomon, the alphabet will be sort of medium sized, something like F2 to the 16. And we want to be able to efficiently deal with this field or any intermediate field. And it's essentially the efficiency of these intermediate fields that makes towers really, really good. I can say just very roughly a few things about what efficient means in this context. Okay, so there's an idea of packing. An F2 to the 16 has essentially 16 bits of information. Okay, so if I have 16 bits and I want to cook up an F2 to the 16 from them, how do I do that? Well, information theoretically, even regardless of how I define this field, F2 to the 16 will arise as a subfield. The question is sort of where does it sit in the big field? And is it efficiently identifiable? So in the univariate case, an element of the subfield just looks like any old degree 127 polynomial. And the fact that it happens to be in the subfield is not something I can just read off by looking at the bits. There's some computation I can run. Essentially, I should iterate the Frobenius automorphism on it and see sort of how large the orbit is. That will tell me the subfield, but that's a computation that you need to run. It's not something you can just read from a linear pass over the bits. Whereas in our case, the subfield elements are exactly the elements whose first 16 bits are non-zero, but the rest are 0. So this is something you can just see. Another really important point is if I have a small field element, a subfield element, and a big field element, can I multiply them faster than a generic multiplication in the big field? So in the univariate case, I essentially have to first embed this thing, which itself has some cost, and then just multiply in the big field. So I'm not exploiting the fact that one of the operands came from the small field. In our case, the cost of this mult is something like 8-fold the cost of an f to the 16 by 2 to the 16 mult. So it grows linearly in the size of the bigger field over the smaller field. And then sort of can I reverse or undo this packing operation? Okay, so in the tower case, these are all essentially free or optimal. In the univariate case, they all have costs. Okay, so our work sort of moving in a slightly different direction, our work also relies heavily on error correcting codes. I won't say too much now, but what I can say that's sort of immediately relevant is that we want to use Reed-Solomon codes. They are MDS, they sort of have the best possible distance given their rate. And they're efficiently encodable, even in the binary field case, as we've seen. This again, I've mentioned this result. The key sort of obstacle, though, is that the alphabet needs to be large. So we're going to discuss a way of getting around this. Okay, so putting some of these ideas together, we can sort of suggest a straw man PCS. So you know, maybe the first question you would ask is can we just treat our F2 elements as if they were F2 to the 128 elements and use breakdown? So obviously, a priori, for a general code with alphabet to the F2 to the 128, even if our message has components that are bits, our code word won't in general. So you're looking at a 128-fold blow up in the size of the code word. Even if we do RS. Okay, so I've already mentioned this sort of in passing. Even in the RS case, we're still looking at a 16-fold blow up. We're exploiting the fact that the alphabet is at least F2 to the 16 and not larger, but we actually want to do even better. So we want, you know, a 1-fold blow up and not 16. Meaning no embedding over it. There is a technical sort of security question that affects not just our project, but any SNARK that uses extension fields, where you actually want to guarantee explicitly that the extractor will extract a polynomial whose coefficients are in the claimed field, right? So it should not be possible for a malicious prover to commit to something that's not actually over F2, but sort of pretend that they did and convince the verifier. Okay, so charging ahead, so getting into how we actually do this, we're going to start with something that looks like breakdown. Okay, so this is a matrix containing the coefficients of some multilinear polynomial over F2. Let's say it's m by m. Now, if we were to apply breakdown now, we would need a strictly binary code with alphabet 0 or 1 or containing that, and then apply that code to these rows, sort of row-wise. What we're going to do instead is a packing type operation. So we're going to go right to left through each row and chunk the elements of each row into 16-bit chunks, let's say. This gives us a new matrix of the same height m, but 16-fold less width, and whose elements are now elements of F2 to the 16 and not F2. Okay, so can we just apply breakdown now? Can we pretend that we were sort of given this polynomial and not that one and just apply breakdown? So the answer is not really, because, you know, I'll sort of skip through the details, but breakdown involves not just a commitment phase, but an evaluation phase, obviously. And if you sort of forget about the original shape of this matrix, then your evaluation is just not going to be meaningful. It will be essentially an evaluation of a totally different polynomial. So there's actually an interplay of these fields that ends up being fairly complicated. Very long story short, you need to sort of do this row combination operation on the unpacked matrix. So first you need to pack it to encode it, but you should sort of forget about that packing for the purposes of the combination. And the final remaining part is that there's this value t that sort of has this shape. It's now going to be of width m and elements in f2 to the 128 that the verifier needs to encode. And it's just not obvious what it means to RS encode this. Recall that our Reed-Solomon code we did use had message length m over 16 and not m. So we sort of the obvious thing that you might want to do sort of essentially looks like this, where you view your f2 to the 128s as sort of chunks of 8 f2 to the 16s, and then look horizontally and RS encode these. So this sort of turns out to be not what you want. Skipping ahead, there's essentially a data layout subtlety that you actually want to do. You want to sort of view this horizontally in chunks of 16, and to get m over 16 total chunks. And then the RS messages you want actually look like this essentially. So looking horizontally, this gives us a vector of f2 to the 16s of length m over 16. So this is sort of the right shape, sort of type checks the way you want to apply RS, which is what we do, and you do that 128 times. Okay, so this actually turns out to be what the verifier does. Now, this is kind of, on the one hand, is a data layout fact. It's also kind of an algebraic fact that we sort of go into in the paper. Now, you actually wind up needing a new proximity gap result. So breakdown relies on a sort of proximity gap for linear codes. You need a sort of variant of that in this sort of new layout, which we do give in the paper. Okay. So I think that's enough for now on the PCS. At this point, I am going to take this for granted, okay, and start progressing to the further layers. So now we should assume that we essentially have the ability to commit to a multilinear polynomial, which for our purposes looks like a giant column of bits, let's say, and then evaluate the polynomial that those bits represent at some arbitrary place. Given that ability, what do we do next? So in the paper, we describe various virtual polynomial constructions, which are essentially ways of manipulating and reshaping committed columns in useful various ways. Okay, so the first is called the packing construction. So here is our picture. Again, we have a committed column of, let's say, 2 to the L bits. And what packing gives us is a way, it's a virtual polynomial, meaning you don't ever need to commit to this right-hand thing explicitly, but essentially using the packing operator, we can, assuming the left-hand thing is committed to, we can act, and proceed as if we also had the right thing committed to, even though we don't. That's what we mean by virtual. So this thing on the right has 64-fold fewer elements, 2 to the L minus 6, but each of the elements are f2 to 64 elements in this sort of packed way. How do we do it? I'll just say in words that essentially you can write down a sum expression involving these coefficients where the sum is sort of taken over the 6-dimensional cube, and where the final sum is exactly this thing. Now, to evaluate that thing at some arbitrary point, you can actually use the sum check, right? So this sort of exactly plugs into what sum check lets you do, right? So after doing a sum check reduction, then the problem of evaluating this somewhere reduces to the problem of evaluating this original thing at some other place, plus some sort of small amount of extra work that the verifier can do. There is a further virtual polynomial that we use a lot called the shift construction. So again, start with the same picture. This is something that's explicitly committed to. Now, the virtual thing we get out looks like the original thing, but with a circular rotation, say, let's say downwards by 3 positions or something, right? So this number 3 can be anything. The shift can actually be circular, or it can actually be a simple shift with 0 filling, up or down. So all of these we support. We actually support a further sort of blockwise shift operation, where in this case, we again segment this into blocks, say of 64 elements, and then each block gets shifted by some amount, let's say 1 or something else. And again, the shift can be circular or with 0 filling up or down. How do we do it? Let's see. Yeah, so first of all, why is this useful? So as we'll see very soon when we get to Keccak, it's often useful to be able to operate over shifted versions of the things we have committed without having to actually commit to those shifted versions. So for example, in Keccak, what you want to do is sort of compare the next round of the main state with the output of some transformations on the current round of state. It's very nice if you can do that without explicitly having to commit to a shifted state vector. And that's sort of exactly what we see. Yep, that's okay. So the complexity is quite good. It's actually independent of the offset. It only depends on the size of the block. So it's actually logarithmic in the size of the block. So in this original example, that would be L. In the blockwise version, it would be 6, essentially, for the verifier. And this essentially answers a problem that HyperPlonk posed. How do we do it? Just very roughly, and I can always come back to this if there are questions. We are able to write down what we call shift indicator polynomials. So these are bivariate polynomials that take values sort of x and y in the cube, or rather just in sort of field to the b. So they're sort of bivariate each. But the key property is that when they happen to reside in the cube, then this thing becomes an indicator that essentially returns 1 if and only if the binary strings x and y differ by an arithmetic sort of unsigned addition of O, where O here is the offset. And the key point is that this is a perfectly good polynomial for arbitrary x and y, but for x and y in the cube, it has this property. And there is a circuit that decides or computes this polynomial whose size is O of b. Okay, so this is a pretty interesting and non-trivial fact. This extends an idea due to Seti, Thaler, and Wabi, where the offset in that case was just 1, but for us it can be arbitrary. Okay, so now stepping yet a further level sort of outwards in terms of the what we're building, I'm going to spend some time now talking about what we call gadgets. So these are sort of assembled sequences of packing, shifting, and various constraints that let you do important tasks. So in particular, unsigned integer arithmetic, so addition and multiplication. We find this to be pretty important because the ability to do these was often cited as a reason not to use binary fields, right? The idea is that if you use prime fields, then you can do these things natively in your field. Now, that actually turns out not to really be true because you have issues with range checks and wraparound and things like that, right? So even protocols that do use a prime field, let's say 32 bits, to add 32-bit integers, you end up needing to break them into limbs, and you can add the limbs natively, but then you need to combine them and do range checks and things like that, right? So even there, it's not really for free. But for us, we need to sort of build these from scratch because we just plain don't have these in the binary field setting. But we do actually turn out to be able to do these. So let's say how. Addition turns out to be very simple over F2, right? So the setup is that we have committed columns X, Y, and Z, say. And the thing we want to prove is that if you go through these columns vertically and chunk each one into 64-bit chunks, then it should hold that chunk-wise, Z is sort of the unsigned arithmetic addition of X and Y is sort of modulo 2 to the 64. And that should hold for each chunk. Okay, so how do we prove this? It turns out that by committing to just one further auxiliary column, C out, okay, so this is the carry out of the addition of X and Y. Turns out that ends up being enough. So we then get C in, carry in, by shifting C out downwards by 1 with 0 filling, right? So note that the first or 0th position in each block should be 0 by definition of what carry in means. And then we just have a few constraints, right? So we need to declare, so this is not really a constraint because C in is virtual, not committed, right? But we want C in to be the shift downwards by 1 position of C out, where the block size is 64, right? And once we have this, we just write down some very simple constraints. So Z should be the addition over F2 of X and Y and C in, right? Where you reduce modulo 2, of course. And then we now need to constrain that C out is correct, which essentially entails requiring that of the 3 columns, X, Y, and carry in, if 2 or more of those are 1, then C out should also be 1. And this turns out to be just a simple expression over F2. Okay, so we're able to add with just 1 auxiliary column, 1 shift, and sort of 2 arithmetic constraints. Okay, so multiplication turns out to be a sort of combination of every idea that we've gone through thus far. So how do you do it? The very rough idea is that we use lookups for limb by limb products, and then we just need to combine those using this schoolbook method, right? The key point here is that for our lookups, we have an adaptation of Lasso for the binary field setting. So this totally works. You need to do a few things differently, but it can be done. So again, here's our picture. We want to multiply X by Y. What we do, so let's imagine that these are 32 bits. And this picture actually tiles sort of horizontally to the right. So we're zooming in now on one 32-bit chunk of our columns, X and Y, which we now write as rows. Okay, so let's segment X and Y into limbs. So let's imagine that these are 8 bits each. And the idea is that we're going to go row by row through the schoolbook method. So in the first row, what do we do? Well, we need to multiply Y0 by each of these things. So let's just not do anything to X. We'll shift it by 0. It's a no-op. We're going to what we call saturate Y at the 0th position. So this is a third virtual polynomial, the saturation operator, which essentially repeats blockwise. It sort of fills Y blockwise with one of its positions, in this case, the 0th. And these are exactly the things we now want to take products of. So we have in green the sort of double width product of X0 and Y0, these 2 limbs. And similarly for X1 and Y0, we have another double width product. And we can write these four things down like this. And the first thing we do is basically use one execution of a lookup to sort of guarantee that these green things actually are the desired double width cross terms. The arguments to the lookup are, shift 0 and sat 0 of y. And now there's a kind of tricky point where how many green things need to be committed to? The answer actually turns out to be not 4, but 2, as this cool animation shows. The idea is that the even and odd substrings of these green values don't overlap. So I can actually commit to all the even ones in one column of bits and all the odd ones in a further column of bits. Okay, so that was the 0th row of schoolbook. Here's the first. So now we actually do shift x by 1. So this is all zeros here. And we saturate y at 1. And again, this is exactly the set of cross terms we want in the first row of schoolbook. Right, so again, we do the same drill, commit to these green things, use one further lookup. And again, actually, I only need to commit to 2, not 3. Moving on to the second row, we shift x by 2 and saturate y at 2. And again, cross terms, a lookup, and finally for the third. Okay, now putting it all together, by definition of how schoolbook works, if we recall all of these green things that we had, this is from the 0th and from the first and from the second and the third. By adding these, that sort of gives us what we want, which is in green. Okay. So what is the complexity? Well, if we write L for the number of limbs per word, we only had to do L lookups, something like 3 times L committed columns, L zero checks, and 2 times L additions. So the key point is that the number of invocations of subprotocols is only linear in L, essentially using this even odd trick. If we didn't have that, it would be something like L squared. A point about the size of the lookup table, right? So in our case, there are 2 to the 16 possible pairs of 2 8-bit limbs. So the size of our table is 2 to the 16. So obviously there's a trade-off here where if you have fewer limbs, then these numbers become smaller. But also the size of your lookup table becomes, bigger very rapidly, right? So if the limbs were 16 bits, then your table would be of size 2 to the 32. Okay, so the final thing I'll talk about is Keccak. And again, our arithmetization for Keccak essentially puts together everything that I've touched on thus far, right? So we end up needing shifting and packing, and also the ability to commit to bits is very crucial, right? So the way we essentially do this is that we only have 60 columns. The Keccak state is essentially something like 25 64-bit values. So we actually unpack those vertically. So we have 64 rows per Keccak state. Since Keccak is 24 rounds, if you multiply this out, you see that we can do 1 Keccak F per around 1,500 rows and 60 columns, as mentioned before. If we allow a total trace size of 2 to the 28, what you find is that you can fit 164,000 Keccaks. The final thing I'll say is just some brief performance benchmark. So what I currently have here is the cost of committing. Our paper also includes other things like cost of prove and verify, and also things like subcheck. But yeah, so it involves Merkle hashing with Grøstl, additive NTT, and of course, binary field arithmetic. And here's essentially the table. This column is commitment cost for polynomial, 28 variables over F2. And you can see that we are, faster by a lot than these other works. Now, the key point is that our work is actually exploiting the fact that the coefficients are small, whereas these works essentially don't. Even when committing F2 to the 8s, let's say, we are still doing quite good. Okay, so that, I guess, is a good place to pause. That's sort of the official presentation, and maybe we can start with questions.
There's a couple of questions from the chat that maybe we want to start with.
Yeah, go for it, Jim. Feel free and run through them.
Yeah, cool. Thanks. So the first one, Maker asked with respect to why binary field Snarks didn't work and relating adjacent trace rows, he asked, isn't there a primitive element for the binary tower too? Do you want to answer that, Ben?
Okay, yes. Okay, that's a good and actually subtle question. So there is, but the orbit of that thing does not interplay nicely with the additive subgroups, right? So yeah, this is actually a non-obvious point. Your trace domain in a binary field, it needs to be an additive subgroup of the field, right? Or really more precisely an F2 vector subspace, okay? If I pick a primitive element and start taking its powers, I'm going to cover sort of everything which is non-zero. Okay, so that's too much. And also it misses zero. But even if I pick some suborbit of that thing, it's going to be completely chaotic. First of all, its order will not be a power of 2. It will be a divisor of 2 to the k minus 1, right? It'll actually be odd. And the elements that I trace through in that orbit are going to interact completely arbitrarily with my additive domain, with my F2 subspace. So it just doesn't give you what you want. And nor can I use that orbit as my domain either, because that will not, if I do that, then I throw away the efficient RS encoding.
Yeah.
Does that answer the question? I can yeah.
Maybe to add one more like way that I think about it, and like an interesting point is like, so if you're working in F2 to the 16, you have a multiplicative subgroup that can like, span, or not span, but like, I guess, cover everything except 0. But if your trace domain is of size 2 to the 18 or something that doesn't align with a tower field, then how are you going to find a subgroup of the multiplicative group of F2 to the 32 that, has size exactly 2 to the 17? That's, not clear. There was another question.
I think my question was next about the implementation of tower fields. So I guess this is general to tower fields and not specific to Binius, but you can do it using quadratic extensions, so f squared, or say f4, f to the 4, for example, at each step of the tower. What are the trade-offs between those?
I can give that a shot.
Okay.
I mean, essentially, the most obvious thing I can see is that it just gives you a less granularity in the sizes of available intermediate fields, right? Which in particular, which intermediate fields can be represented as a sort of with a multilinear basis, right? So your basis will not be multilinear anymore for certain intermediate fields.
Although, I mean, it's every even-sized field, basically, if it was up to 4. So that's probably sufficient, I think, unless you want to use individual bits.
So I think there's So there's a couple of reasons. It's a great question. But so the first is we use this specific like Wiedemann tower, which gives a sequence of quadratic extensions. And so first you would have to like go and find how you're going to pick your quartic extensions and hopefully have something that has the same structure. And then the other thing is like, because of the specific properties of this tower field, you asked another question related to this.
Yeah,
but like,
yeah, I was going to ask that. What exactly are you depending on about the Wiedemann towers? Is it that the reducible polynomials are very regular? They're the same at so modulo the indices at each step, or?
Yeah, Ben, do you want to like try to explain why you
catch.
actually get this efficient multiplication for the Wiedemann tower?
Okay. The question is, where does the efficiency benefit come from?
Yeah.
Okay, let's just say a few quick things. I can try to run back. It's gonna take a while.
But basically, what are you relying on from that that way of constructing the tower?
Yes. Yeah. So, sorry, just give it a second. Here we are. Okay, so the very, very quick way to say this is that what do you have to do when you multiply? Well, if I want to multiply two elements of this field ring, right, then they both look like degree 1 polynomials whose entries are in the smaller field down, right? So first I need to multiply two linear polynomials, get something quadratic, and then I need to reduce that quadratic thing, okay? Modulo this. And everything ends up being exactly the same up until the point when you reduce, okay? So in other words, the benefit of this only kicks in a very, very specific point, which is when I reduce. So I have an arbitrary quadratic polynomial, and I want to reduce it modulo this particular quadratic polynomial. What does that entail? Well, whatever the leading coefficient of my given thing is, I need to multiply this by that leading coefficient and then subtract it, right? So, call it alpha or something. I have alpha x iota minus 1 squared plus something else. So I need to multiply this whole thing by alpha and then knock that out, right? And the key fact here is that the coefficient x iota minus 2, so the key problem ends up being multiplying this particular thing by alpha. And what's true in Wiedemann's tower, but not in other towers, is that multiplication by this particular element is more efficient than multiplying by an arbitrary element, right? So there's a way of multiplying by this particular thing that is much cheaper than, right? So for general f, this thing, instead of being x iota minus 2, would be something arbitrary, right? And it's just simply cheaper to multiply by this. Why? Well, because it's a very simple monomial. It's kind of just like a shift, and it sort of just checks out. Does that answer enough? Or I can...
Yeah, the rest I can look up. Yeah, thank you.
It is worth noting that we actually originally found another form of this sort of deterministically iterated tower basis that was like an Arden Schreier tower that gives you, better than quadratic multiplication time, but it was, the asymptotics were somewhere between the Fan-Par tower and quadratic, and we, basically stumbled upon this one instead and decided to switch.
Yeah. So it's basically just that you need efficient multiplication. It's not an interaction between this representation and the rest of the
Yes,
scheme.
exactly. It's completely opaque to the every higher part of the scheme, which polynomial you use. It's just for efficiency.
Okay, cool. Thanks.
But one more thing to say on the arithmetization, I can basically make arguments as to why you would like to have the subfields of like 8 bits, 16 bits, 32 bits, and 64 bits. Like they all have, the 8-bit field's nice if you're doing AES arithmetization. The 16-bit field is nice for Reed-Solomon encoding in our breakdown scheme. Like we were actually able to make use of all those intermediate fields.
Yeah, I think I'd been underestimating the benefit of that. Yeah, good point. You do need all of 8, 16, 32, and 64 to express lots of interesting algorithms.
You asked a bunch of questions, so do you have any others that you wanted to follow up on and ask now?
I'm just looking at the history. Yeah, I was just noting that lots of functions and ciphers rely heavily on shifts. A question about carries was answered.
Another code to read Solomon. I actually don't remember what.
Is it something like, was it cluster or
Concatenated codes, perhaps?
I can't remember now.
Yeah, I didn't catch it either when I saw the question.
Okay,
so
doesn't matter.
Yeah, Victor asked a good question about how we're able to do a version of the shift polynomials that instead of doing a circular shift, like sort of is an arithmetic or logical shift that like basically zero fills. Do you want to say anything about that, Ben?
Yeah, so actually, it turns out that the non-circular shifts are simpler, actually. What ends up happening internally when you look at how we define our shift, what ends up happening is we actually define a sort of downward shift and an upward shift. And actually, the circular shift ends up being the literal sum of those two things. The problem is not actually setting bits zero. They just kind of are zero by how downward and upward shift work, right? And so to really answer that question, you kind of need to go into how the downward and upward shifts work, right? And of course, the circular shift ends up being a sum of those. But I can just say in essentially one sentence or so, the way downward shift works is by writing down a shift indicator where it only returns 1 if sort of y is below x by, O steps, right? But not above it by, 32 minus O or something, right? And then the upward shift is like the opposite of that, right? So it's actually the sum of those that ends up being the circular shift. Can I say more on that, or is that satisfying?
That seems good to me. Thank you.
Okay, yeah, happy to follow up further if you have any questions on shifting.
Marcus asked, do we see potential for new zk-friendly hash functions which operate natively over binary extension fields? I certainly do. So, I mean, one, I think, promising benefit of this is that we will be able to efficiently arithmetize classical hash functions, but if you're doing I think there's still a benefit to having even more arithmetization optimized hash functions. So to leak a little bit of alpha, we are investigating using the vision construction over the 32-bit tower field and seeing if there's optimizations we can find to that. And however, I know that you are also, well, you're an expert in symmetric cryptography, and I'm far from that. So if you would like to chat with us about arithmetization optimized hash functions over tower fields, that's something that we are quite interested in.
Yeah, I mean, obviously some ciphers already and hash functions already use binary fields. I mean, AAS and yeah, so because multiplication in a binary field is less efficient on a conventional processor than it is here. Yeah, I think there's still some scope for improvement there, because the trade-offs are not exactly the same between this and conventional processors.
Yeah, we're working on we are actively working on our open source Rust software implementation of the Binius system, and some of the, working towards implementing arithmetizations of various hashers. So, Keccak, SHA-2, and Grøstl, which I cannot pronounce as well as Ben, but which uses the AES SBox and seems to be, fairly arithmetization optimized for this setting. But
Have you looked at any of the Blake family?
not as closely, but like I'd love to have, hash verification gadgets for everything. And I know that Blake is very just, CPU friendly and optimized.
It looks like it will be very, very fast on this, because you can do additions, regular 2 to the 32 efficiently. You can do shifts, and you can do XOR, and that's really all you need for the inner function of the Blake and Cha-Cha families. So yeah, I'm not even sure how you could improve on that with you probably could improve on it by natively using binary multiplication.
Yep. Binyi, do you want to ask your question aloud? Otherwise, I can repeat it here. Binyi says, it seems the main reason we can't use Fry is because we can't have a large multiplicative subgroup, but what if we use the basefold IOPP that can support non-FFT friendly fields? I can say that, so the original Fry paper, actually kind of the headline result is about Fry for binary fields over additive subspaces. And that is not lost on us. We have some more investigating to do to see how much we can adapt that to our setting and find optimizations. We are optimistic, but not ready to share results right now. Verena, I don't know if I'm pronouncing that right. Also, Binny, if you want to chat with us about that, we can certainly get in touch. Verena asks, do you want to ask your question aloud?
I don't mind if you can hear me.
Yeah. Yes.
Okay, yeah, so you were mentioning in the introduction that you also considered binary codes, and I was just wondering what issues you faced there, or what your considerations were, or if you also considered any other error correcting codes besides resolving.
Yeah, so I can take a shot at this, Jim.
Please.
Yeah, so this is a good question, and we definitely have a fair amount to say. Essentially, it is simply not that easy to construct binary codes with very small alphabets. And after looking around, it seems that the sort of most natural construction is what's called concatenated codes. These are essentially a way of sort of bootstrapping a Reed, well, to very oversimplify, they're a way of bootstrapping a Reed-Solomon code to a code over a tiny alphabet by sort of concatenating in front of a very, very small binary code, right? So the idea is that if I have, let's say, a 3216 code over F2, right? So maps 16 bits to 32 bits. If I have that, then I can sort of concatenate that with the Reed-Solomon code with alphabet F2 to the 16, and out comes an actual binary code whose distance is actually quite good. So one thing that you can do, which we totally describe in the paper, is actually use a sort of simpler breakdown, like a plain breakdown without packing, where your code is a concatenated code, or any binary code. And this actually works perfectly well, and it might even be more efficient, at least in terms of proof size, than what we do, namely with packing. And we actually give some benchmarks for precisely this construction. Now, what's the downside? Well, everything I said sounds pretty good. The essential downside is that the concatenated code construction it is not an asymptotic construction. It requires that you supply this tiny code, this sort of small code over F2 is completely ad hoc. And you need to sort of supply that for each size of the Reed-Solomon code you get. So in particular, it just simply doesn't even make sense to say, how does a concatenated code approach perform asymptotically, let's say, right? Because we just don't have a way of coming up with asymptotically good codes over F2. The only thing you can do is sort of plug in the best binary code you can find at each step. So there's a kind of theoretical challenge there. Also, much more down-to-earth reason is that it's just plain simpler efficiency or implementation-wise for, let's say, the verifier, when the verifier does not have to perform the encoding function of this arbitrary ad hoc inner binary code. So there are implementation considerations, asymptotic sort of theoretical reasons, and various things like that. There might be some better code, some better binary code than a concatenated code. I don't know of any, but it's definitely something you can do that we just opted not to do for various reasons. Does that answer, or?
Yes, thanks very much for explaining those.
Yeah, I want to add a couple things. I think that's spot on. Another choice that you might wonder about is the Spielman linear time encodable code that is described in Brakedown and some other works. Like Brakedown gives this construction of like a randomized expander code, and we actually looked into this a lot early on, and sort of the memory access patterns of doing these random memory accesses just didn't lend itself to a nice implementation, and we have like a lot of experience optimizing NTTs in software and hardware, and the memory access pattern is like well studied, and so we like Reed-Solomon codes. We just like Reed-Solomon codes. The other thing is that I'm not sure Ben mentioned is there's an improved proximity gap result for Reed-Solomon codes specifically that's better than the best proven proximity gap for general linear codes. So that, gives you a little bit of a boost as well. And then, yeah, Ben mentioned the point about implementation efficiency, but that's like very important to us as, having a large engineering team, that like the overhead of doing this inner code encoding is just kind of a pain.
Should we turn to Benedict, who has very patiently sat with his hand raised? Benedict, did you want to articulate a question?
Yeah, thank you. I guess I feel like there's some basic misunderstanding here. Why couldn't I just use, so for the multiplication, exactly the slide of, why can't I just use just fast polynomial multiplication and then reduce mod the, no, I meant actually the slide that you were already on.
Sorry.
Yeah, why can't I just use fast polynomial multiplication and then reduce mod the, I guess, fi or whatever? What am I missing? Like
in this ring, you mean in t iota, fti?
Yeah.
So the two polynomials you're multiplying are of degree 1, right?
So the basis, like we're used to thinking about binary fields as having as being univariate polynomials. Our basis for the tower fields are a multilinear polynomial basis, right? So and then you can still do pointwise multiplication. That is absolutely true, but it's very unclear how you then do the reduction and like what you're then reducing. I'm not saying it's like impossible or I don't know, but like it's very unclear what doing that reduction would then look like.
Okay, I guess you're saying this. Okay. This is the I guess there's, at least in theory, there's algorithms still though that should be faster than what I guess is like n to the 1.5. like, I mean, there's just like fancier multiplication algorithms over just generic.
I believe you
like
can
super
do
generic,
this.
right?
Yes. I think if you use very fancy things, you can beat this asymptotically. We have not really gone down that path. So yeah, let me just try to clarify as much as I can. Essentially, elements of this ring are polynomials of degree 1 or less in t iota minus 1. Now, as Jim said, if I take this ring and unroll all definitions, this turns into a multivariate polynomial ring, where the elements look like multivariate polynomials in x iota minus 1 ... x0, where the degree of every indeterminate is 1 or 0. So they're multilinear. Now that's fundamentally the object you want to multiply. When I talk about Karatsuba, what I mean is I sort of group them. I pretend that they were linear, where essentially I group everything that is of lower than x iota minus 1 into the coefficients and act as if those were linear polynomials. But yeah, it's true that there are sort of fast techniques even for towers. I think that you should be able to get to n log n instead of what we have here. I think there's a work by DeFeo, Schost, and one other, I can't remember, that where I'm pretty sure they claim an n log n asymptotic complexity for the tower setting. So we just simply haven't.
Like, and as a practical algorithm, like not just using like Schön-Hagelstraßen generic multiplication.
So I can't tell you specifically how they do it, but yeah, I believe that they are claiming that it's sort of more down to earth than what Schön-Hagelstraßen do. But actually, I think the substance of it ends up being a conversion or some kind of field isomorphism between this and something univariate, where in the univariate setting, you can then fall back to whatever classical fast thing you want. And they claim that there's an n log n time conversion between the multilinear representation and some kind of monomial representation. This is, I wish I could say more about how they do that, but yeah, I believe it's more down to earth. For our purposes, we just simply didn't find a huge need, because actually, concretely, we get quite good efficiency with just a simple tower. With Karatsuba, I think we're, sorry?
Interesting. That was my next question, like whether this matters in practice.
Yeah, I think we are maybe a couple fold slower than a pure monomial basis multiplication with Karatsuba. Does that sound right, Jim?
It depends on the platform. So one thing we haven't mentioned yet is that Ulvetanna does FPGA implementations of various cryptographic primitives. So we look at the efficiency of these things from perspective of both CPU implementation and kind of native digital logic. I believe I would need to check with our hardware engineer that for the 128-bit tower field, which is sort of our largest field that we're using in our implementation, that the univariate sort of basis that the ghash AES GCM mode uses is only like 10% more efficient than our 128-bit tower basis in digital logic. It is, however, considerably faster on the CPU because there's just a faster reduction. So our CPU implementation of the tower fields will, I think, be doing more to publish like the kind of SIMD algorithm we use for this, but relies on Intel's Galois field native instructions, which do 8-bit, or they do, there's instructions to multiply 8-bit binary fields in univariate basis, and we sort of build up the recursive multiplication on top of that primitive instruction.
I was going to ask where do you start the recursion from? So yeah, I guess it makes sense to start it from 2 to the 8.
Yeah, we're also looking at you know, on machines that don't have that instruction, we're investigating what we can do. We're working on a CUDA implementation right now. Actually, the person working on that's on this call, but so we'll have more to say on efficiency on different platforms that don't have the GFNI instructions soon, hopefully.
Yeah, I mean, I guess you can implement those using lookup tables anyway, even if you don't have instructions.
We have an algorithm that sort of, you can do kind of fancy bit twiddling stuff to transpose things in a cool way. And I think that's the best we've come up with so far. But, you know, what we really care about is the efficiency of this stuff in native digital logic, because, you know, we think that ultimately, well, in the short term, we will have FPGA implementations for the computational bottlenecks of this proof system, and in the long term, you know, custom silicon. Bin-Yi probably has had his hand up for a while.
Yeah,
Thank
Bin-Yi,
you.
you want to go next, and then Dara.
Thank you. Sorry, I was having some background noise, so I didn't reply. And yeah, it's good talk. And really sorry that I've missed the first half of the talk because of some other issues. So, I may have some misunderstanding. The main question I have is about the packing techniques. So I've heard that you are anyway using the Reed-Solomon code for the PCS. So my main question is, what's the motivation of using Brakedown in the first place? It seems that more natural to consider Fry if you are using Reed-Solomon code for PCS. So is there any like subtleties at the beginning when you decide that you will use Brakedown rather than Fry for constructing a PCS that combine with this packing technique?
Yes. Maybe Ben, can I take a stab at answering this
Yeah,
first, and you can go into some detail. So when we started working on this, so Fry is as you well know, Fry is an IOP of proximity. It's not a polynomial commitment scheme. There's like a pretty well-known at this point transformation for using Fry to construct a univariate polynomial commitment scheme. And then there's a HyperPlonk, your paper gave a nice way to do a multivariate polynomial commitment scheme using the Fry, well, using a multilinear polynomial commitment scheme using a univariate polynomial commitment scheme. Now, the univariate polynomial commitment scheme that uses Fry uses the technique of quotienting, which means that you actually interpret the sort of values of your Reed-Solomon code word as kind of useful information, and that's basically incompatible with our packing technique, because we're in the way that we're packing bits into you know, Reed-Solomon code word symbols, it sort of corrupts the meaning of them in a way that is not compatible with the quotienting, like deep Fry methodology. And so that's why we looked at Brakedown, because Brakedown and the tensor code approach strongly decouples like what part of the PCS is using the coding theory and like how you're doing the evaluation.
I see. That's really interesting. So basically, it's the quotienting becoming the bottleneck. So
Yes.
what if, like, for example, there are some other compilation from IOPP to PCS, for example, like in base4, there's a sum-check based compilation. So is sum-check will be compatible with that?
We think that's a very cool construction, and we would love to chat about it offline.
Sounds good. Yeah, thank you. Yeah, that's really helpful. Thank you so much.
Ben, did you have anything that you wanted to add here?
No, yeah, I think that covers it, right? Essentially, you're then forced to choose between either don't pack, but then you have embedding overhead, right? Where you're embedding your bits into F2 to the 16s, or do pack, but then you've corrupted the meaning of your code word, something like that, right?
I see. Thank you.
Yeah, I think part of my question has been answered by that, but so yeah, it might be worth looking at hybrids of some of the existing polynomial commitment schemes that satisfy the constraint that you need for packing, but that pick and choose ideas from them.
Yeah, to say one more thing, we think that this is you know, at least worth investigating. However, it is another thing that makes us like Brakedown is that you are rearranging your matrix. So let's say you need to commit a matrix polynomial of size like 2 to the 28 or 2 to the 30 or something. With Fry, you would need to do a Reed-Solomon encoding with a block length of something around that size of 2 to the 30. And so you would need to use the 32-bit tower field because your field needs to be larger than the block length of the code. With Brakedown, it shapes the matrix, it shapes the multilinear polynomial into a matrix, and so your Reed-Solomon code words can be smaller. So to commit a 2 to the 30 size polynomial, you might likely be able to do Reed-Solomon encodings with a block length of 2 to the 16 or less, which means that you can use the 16-bit tower field and get, you know, a pretty significant efficiency advantage from doing that. So that's you know, for workloads where you can afford to have larger proofs and faster proving, there's still a good reason to do that, in my opinion.
Yeah, so the reshaping has this sort of side benefit where you have a square root reduction in the message length that you want to encode, and then that in turn lets you use smaller alphabets.
Dyra?
Dara, was that your question, or did you have another question?
I think my question had already been answered.
Great. And then I think next is Victor.
Yeah. Have y'all done any experiments so far, or at least have intuitions on what like self-recursion might look like? And if you, well, I guess first of all, if you can self-recurse efficiently, and then if you do, if you'll actually get any kind of size reduction in the proof after doing more than one layer of that. Does that make sense?
Yes, the question makes sense.
Okay.
I'm happy to take a stab. Like, we don't have anything concrete to say about this, except that we're like optimistic that, you know, we're kind of starting with, we're building the software implementation of the arithmetization. We give a concrete and fully described arithmetization of Keccak in Appendix A of the paper, which, as Ben said, we think has like very low overhead over the Keccak, you know, like the amount of data that you need to commit for this is, you know, pretty low compared to the Keccak state itself. So figuring out what our arithmetization cost for hashers is prerequisite to us figuring out the arithmetization cost for self-recursion. And this is where stuff like, you know, possibly investigating arithmetization or optimized hash functions over tower fields is interesting.
So for recursion, how many hashes basically would you have to do how does it depend on the circuit size?
Asymptotically square root.
Okay. Oh, that's pretty good.
Yeah, so I think, I mean,
Okay.
I don't remember the numbers offhand, but like Ben, in the paper, we gave some kind of like proof sizes, and basically we were getting compression of what, something like 500 megabytes to 10 megabytes, or let me see if I can pull this up in the paper.
It goes from 512 to between 7 and 11, depending on some details. And then we can also compress 8 gigabits to around 60 megabits.
Yeah. But
Okay.
yeah, I mean, definitely still interested in doing research on like what other trade-offs we could be able to strike in terms of proof size, proving time, and hopefully have more to say on that soon.
Yeah, I'm definitely looking forward to that.
Awesome. I have one last question, and then we can close because I think we're at time. You mentioned in the talk, you know, I think we talked concretely a lot about prover performance, but you mentioned when discussing Snarks, you know, some of the reasons why in practice you're constrained is just the network overhead. Can you say anything about the verifier cost and the proof sizes in this scheme? relative to maybe, I guess, existing deployed schemes. And the reason I'm asking this is because in a lot of applications, like proving is obviously the biggest overall cost, but for depending on the application, particularly the public blockchain setting for like rollups, e.g., like the verifier cost is pretty meaningful, economically speaking.
Absolutely. Ben, do you want to take this because you have the slide up?
Yeah, sure. So I can say that after one level of recursion, so we were just discussing this, that we do achieve a many order of magnitude compression rate in the size. So we, as we just said, we can compress 512 megabits to say around 8 megabits in one level. We can also compress 8 gigabits to around 50 to 60 megabits in one level. So I think that in practice, you would not use, say, just one level of recursion. You would use either multiple or maybe compose with something else. But I think we believe that we have achieved some sort of escape velocity where we have enough compression to make recursion work and to yield, possibly after composition with something else, something which is feasible in practice. Jim, maybe you can add to that.
Yeah, one clarification. Did you mean megabytes and gigabytes, or was that intentional to say megabits and gigabits?
I guess what I really meant was GI_b, so Gibby bytes.
Yeah, those are bytes. And then I think maybe the missing thing to make explicit here is we like basically believe in, Ben, could you like forward to the next slide with the zkEVM chart? Yeah, the one back. Like this on the right. So this is basically a diagram that Polygon published of like their overall proof system. And we basically believe in this architecture, which is like the bulk of your proving you're doing in a proof system that has a fast prover and a, relatively expensive verifier. And then you have several layers of recursion that ultimately ends in a super, small proof, fast verifier, elliptic curve snark, but over a very compressed, recursive statement. And then there's several, who knows how many you actually need, but like layers of recursion in between where you're kind of progressively compressing more aggressively. So we do think that for many applications, like this sort of hybrid scheme where you're going to do a bunch of binary proofs and then you're going to like do a recursive elliptic curve snark proof at the end to say, put it on chain or, whatever, it is likely, it seems to be a winning paradigm to us right now.
Yeah, so if you use an elliptic curve proof, then you lose the post-quantum security. I guess if you use PLONKi 2, then that's probably the smallest and most efficient to verify post-quantum proof at the moment, I think. Could be wrong.
Yeah. We'd like to certainly be able to get like the native binary field proofs under 100 kilobytes, and then it's sort of up to you if you're like, I'm not sure.
Yeah, no, it's super helpful, right? Because I mean, you can just think of like the Ethereum throughput, right? Like, if a proof is existing on chain, you can think of, okay, like how big is a block and then how big are proofs, right? So this like at least for a layer 1 public blockchain setting, right? If you're thinking of other settings, this doesn't apply maybe, but like for blockchain, obviously proof like block sizes and time per block is really, because the network bandwidth that you need to have, like every node sending every proof to every other node and verify, it ends up becoming, in my experience, at least with Aleo, dominant at some point. So that's at least on the network level. Obviously not on the prover level, but the whole network isn't bearing the prover cost, right? That's only like one person that can take as long as it wants. But super helpful. And this is a great talk. Thank you very much for putting this presentation together. Thank you everyone for attending. And with that, I would just love to say, just a big thanks, and hopefully we'll get to see everybody next time. Jim and Ben, any final words before we conclude?
Thank you so much for having us. Ben, did you?
Yeah, just saying, appreciate you having us on, and thanks for the opportunity.
And we're hiring engineers who know cryptography.